Assalamualaikum and hello everyone. I am Muhammad Azim Kwamin Hakim, your top tutor here at University Technology Petronas. Today, we are going to explore one of the most elegant and powerful results in vector calculus, Stokes Theorem. This theorem is a bridge. It connects line, integral and surface integrals, helping us understand and how circulation around a boundary relates to rotation with a surface. By the end of this short lecture, you will understand not only the theory but also how to apply it in solving real problems from engineering to fluid dynamics. Let's dive in.
Continue to the next part. I will explain to you guys about the Stokes Theorem component. Okay, so as you can see, there are the formal statement of the Stokes Theorem here. For the component C, it is a closed curve, which is the boundary of the surface of S. For S, it is a surface bounded by C. And there is also F, which they are in the two components in the formal statement, which is the first one is a vector field, and the other one it is the curl of a vector field, which representing its rotation. And there's also the n symbol that represent the unit normal vector to the surface. In a simple word, the total circulation of a vector field around the boundary curve equals the total rotation, which is the curl of the field across the surface enclosed by that curve. Imagine the loop of a wire in magnetic field where the circulation around the wire is directly related to how the magnetic field swirls through the surface it encloses. This is the essence of the Stokes Theorem. That's all for this part. So we get the answer for f.dr is -1, and then we continue the equation that we learned of the formula of f.dr, right? So we're just gonna put it, if the limit is the 2 pi and here is 0, so we're just gonna put -1 dt. And then we just gonna have the answer for this is just negative x negative t. So we get the f.dr is -1. We compute it in the formula. It's 2 pi and 0. We get here -1, right? So it's gonna be dt. So it's gonna be dt. So it's negative t. So it's gonna be 2 pi 0. Sorry, so we're gonna get negative 2 pi minus 0. So the answer for this is negative 2 pi. We're not done yet, so it is just for the line integral. So we're going to continue for the surface integral. So for the surface integral, we're going to do, so we're going to continue with the surface integral. So we're going to find with this equation. First we're going to do the cross product of this, which is the curl of vector field, which is the cross product. So the cross product is the do dx, do dy, d over dz. So this will be dy, dt x is 0. answer is 0, -2. So we're gonna find already for the dot product with the normal. So 0, 0, -2. Product 0, 0, 1. We're at -2. Put it up in the equation on the equation that we wrote here. Just put it -2 pi. So it is proven that how the Stokes theorem works.
Now, let's try a slightly more challenging example. Let f equals to yz, sz, xy, and let S be the portion of the plane x plus y plus z equal to 1 above the xy plane, bounded by the coordinate axis. First, we compute del times f, which we will get x minus zi minus y minus xj plus z minus yk. Then, we will find the normal vector and surface limits. For the plane x plus y plus z equals to 1, we will get z equals to 1 minus x minus y. And then we will get n equal to 1 over sec 3 times 1, 1, 1. The projection on the xy plane is a triangle with vertices at 0, 0, 1, 0 and 0, 1. After that, we will substitute and compute the flux. After simplifying, we will get the answer, which is 1 over 6. This shows how Stokes' theorem works, even for non-flat surfaces. Now, let's see how Stokes' theorem applies in the real world. In electromagnetism, Faraday's law of induction uses Stokes' theorem directly, as we can see in the equation. This means the circulation of the electric field around a loop equals the rate of change of magnetic flux through that loop, the principle behind electric generators and transformers. So when you rotate a coil in the magnetic field and generate electricity, you are literally applying Stokes' theorem in action. Now, this is a question regarding the real-world problem using Stokes' theorem. A wind turbine generator contains a circular coil of radius 0.5 meter that rotates inside a magnetic field. At a certain moment, the magnetic flux passing through the coil is increasing at the rate of 0.2 Weber per second due to the rotation of the blades. Using Stokes' theorem, determine the induced electric field around the edge of the coil. We are given the radius and the rate of change. So we can directly apply the value in the equation. Using simple calculation, we will now get the value of the circulated electric field, which is 0.064 volt per meter around the coil.
Let's address some common question from students.
How do I know which surface to choose for S?
The answer is any surface with the same boundary C will give the same result because the theorem depends only on the boundary, not the shape of the surface. So, next question please.
What's the physical meaning of curl in this context?
Curl measures how much a vector field rotates or swirls around a point. Stokes' theorem connects this tiny rotation to the total circulation around the boundary. Okay, next. Final question maybe?
Can we use Stokes theorem in 2D problems?
Yes, in 2D, it reduces to Green's theorem, which relates a line integral around a closed curve to a double integral over the region inside. To sum up, Stokes theorem links line integral and surface integral. It's a powerful tool for simplifying vector calculus problem, and it has deep connection to real physical phenomena like electromagnetism. Thank you for watching. Hope this session helps you visualize and apply Stokes theorem confidently. Don't forget to like, share and subscribe to your learning channel. See you in the next lecture.